One of the real power of the idea of the scalar electrical potential is illustrated by this problem, number 27. Now in this problem here, they show an arrangement of 3 charges here, all 2 nanocoulombs, arranged on corners of a square, and they'd like to know the electric potential right here at this point. Now the first thing that might pop your head is, didn't I just do a problem like this? Wasn't number 5 a problem like this? Yes, number 5 was like that, but number 5 was the electric potential energy. That is not the same as electric potential. We just want to know now what is the electric potential at this point here. No energy after the word, just electric potential. So in other words, it gets to a concept we try to get across in class, that if you have an arrangement of charges in space, the charges set up a potential field in all space around them, and we just like to know it at this point right here. You can imagine this was your black paper from the laboratory where this was a charge, this was a charge, and this was a charge, and you put your voltmeter probe, what reading would you get here? The power of those scalar potential is as follows. Scalar potential, there's no vectors. If we're asking for the electric field here, we need to do a big vector addition at this point, but it's scalar potential. So all we have to do is figure the electric potential at this point due to all of these charges here, and we'll have our answer. Just add them together. Let's call this charge 1, charge 2, and charge 3. So the scalar potential at this point, the answer to this problem here, is the scalar potential at this point due to charge 1 plus the scalar potential due to charge 2 plus the scalar potential due to charge 3. If you can just find V1, 2, and 3, you just add them together as numbers and you'll have your answer. No vectors required. We know from class that the scalar potential due to a point charge is given by a formula that sort of looks like this here. V is equal to K times the charge amount divided by R. So if you have some charge Q and your distance R from it, this is the scalar potential or the amount of volts that it will have induced or make occur at the particular point in space, a distance R from it. So we can just use this equation and sort of fill this bottom one in here, start to get our answer here. So the potential then will be the potential due to charge 1. So I'll do a K times, say, Q1, the charge on this Q right here, divided by the distance from it, which in this case would be this distance right here, or the 3 centimeters, or the 0.03 meters. No squaring required here. It's not an electric field, so you just have a 0.03 not squared. Plus the scalar potential due to charge 2, so it'll be K times Q2. And now Q2 is up here. How far away from Q2? I'll let you compute that, but it'll come from Pythagorean theorem, so I'll just label it for right now R from charge 2. And it's definitely, as I said, this sort of diagonal distance right here that goes all the way across, and maybe your distance will be a bit straighter than mine was. Yes, it will be this distance right here. This is R2. And lastly, we add in the scalar potential due to charge 3, which we just put another K times Q3, and the distance between the point in question and charge 3 is just one of the sides of the triangle here at 4 centimeters, 0.04 meters in there. So there's your answer right there. The scalar potential at this point is none other than the sum of the individual potentials created by the other 3 charges sitting around like that in a superposition problem. And I believe if we put in all the numbers on that and do a bit of calculation on there, you get something like 1,410 volts. So the scalar potential is 1,410 volts. That's what you'll get there.